This next problem is all about converting mass to weight. So before we start this problem, just want to go through in a little bit more detail to define what's the difference between mass and weight. So in everyday English, we use these two terms interchangeably. So you'd say my mass, 70 kilos, I wish, and my weight, also 70 kilos. So basically mass and weight, when we're using it in everyday English, is the same thing. That's not the case in engineering problems, so mass and weight are very different. So mass is pretty much what we think of when we say either mass or weight in English. So let me just illustrate this with a bit of a sketch. So first thing is I'll just draw the Earth. Okay, we'll get America, South America, Africa, a bit of Europe, Norway's up here somewhere, and we have to make sure we don't forget Scotland. Really, we should be drawing Australia here, shouldn't we? There's Australia poking it there. Okay, New Zealand, don't forget New Zealand. Now, also just draw the moon, and a few craters on the moon. And then we also want to draw something that's very, very far away. Now, what you do in engineering drawings is if you don't have space, you can show that you've cut out a bit of space by drawing a line like that. Use it in engineering drawings. So now we're out in space, just stars, and the stars are far enough away that we're not feeling their gravity. Now, suppose on Earth we've got a little red box. I might make it a bit, this is not to scale, obviously, otherwise it's squashing quite a few people in America, or maybe Canada up there. A little red box. And let's say the mass of that little red box is 20 kilograms. So mass is 20 kilograms. Now, the mass of that little box doesn't change, doesn't matter where you are, it just depends on how much material is in that object. And so if we were to take our little box on Earth, it's got a mass of 20 kilograms. Move it up to the moon, still got a mass of 20 kilograms. Put it into outer space, where it floats around, still got a mass of 20 kilograms. What changes in these different places is the weight. So the weight of an object, let's just bring that down and do a close-up of it sitting on the Earth. So we'll just draw the ground. Another engineering shortcut is when you want to draw the ground, you just draw a line with some little lines underneath it, showing that this is the ground. So the weight of that, as opposed to its mass, the weight of that box is the force that gravity pulls it downwards with. So it's this force acting downwards, that's a weight, and the units of weight are newtons because it's a force. Another way to think about it, you could think about that as it's the force that the ground has to exert upwards to keep that little red box in place. So again, it's a force, it's going to be given in newtons, or it might be in kilonewtons. Could even be in meganewtons, depends how big the box is. And so, but the key point is mass is in kilograms, weight is a force, it's in newtons. Now that weight can change depending on where it is. So if we were to take that little box, put it on Earth, it's going to have one weight. Take it up to the moon, let me just move that back down again, sorry. Take it up to the moon, it's going to have a smaller weight because the gravity on the moon is less than gravity on Earth. Take that box and put it into outer space, it's now got no weight at all, just floating around, there's no gravity. Okay, so let's come back to the Earth. So we want to calculate the weight from the mass. So we know on Earth, gravity is equal to 9.81 meters per second squared. Sorry, I keep moving the page around. Now, gravity does change a little bit on Earth depending on where you are. I've lost my little red box. Let me just get that box back so it's red again. Can't. That'll do. So gravity on the Earth 9.81 meters per second squared. You can also write that as meters times second to the minus 2, but I'll just use meters per second squared. You want to calculate, let's actually just change this. We'll just make this GE because we're going to be talking about the gravity on the moon in a minute. So let's call that GE is equal to 9.81 meters per second squared. To get the weight of an object, you're just doing weight is equal to mass times gravity. In our case, our little box weighs 20 kilograms. Now you have to use kilograms in this equation unless you're doing a bit of a shortcut, which I'll tell you about later. So 20 times 9.81, which is equal to, so we'll just bring up, we've got a little calc pad here. Oh, I've already done it. 20 times 9.81 is 196.2. 196.2 units. Weight's a force. It's in newtons. Unless you try to make a shortcut in here, which again I'll tell you about later. So if you use this equation, the best thing to do is just use kilograms. So put kilograms in here, times it by the acceleration due to gravity. So that's this 9.81 meters per second squared, and we're going to get the force in newtons, which is the same as the weight of that object, 196.2 newtons. Okay. Now, suppose we take that little box, we put it on the moon. Let's calculate the mass of that box when it's on the moon. Did I just say mass? The weight of the box when it's on the moon. The mass of the box when it's on the moon is still 20 kilograms. So, the gravity on the moon, GM, is equal to, it's about a sixth of the gravity on Earth. So let's just get our little calc pad up. So 9.81 times 1 divided by 6. So it's about 1.64. I think it's actually 1.61, but anyway, we'll run with 1.64. It's approximately 1.64 meters per second squared. Now again, this gravitational constant is given as an acceleration, and we'll talk about why that's the case when we get to dynamics later in the course. So W is just equal to, so the weight of an object is just its mass times the acceleration due to gravity. In our case, the mass of our box is 20 kilograms. On the moon, the acceleration due to gravity is 1.64. Oh, I won't write their units in. 1.64. So the weight of that little box on the moon, bring up our calc pad again, we should be able to do this in our heads. It's going to be 32.8 newtons. It's a force, it's in newtons. Let's just check that because my mental arithmetic is shockingly bad. So what did we say? 20 times 1.64, 32.8. Not so bad actually after all. Okay, now take the box. Trivial question, but take your little box and put it in space. This time gravity in space is 0. Therefore your weight is equal to mass times gravity. Doesn't matter what the mass is, you're doing mass times 0, which is 0. So something is weightless. That's why they call it weightless when you're in space. I've turned my little red box black again. Okay, bring them back to Earth. So that's the basics. So what are we saying? Mass measured in kilograms never changes. Weight measured in newtons. It's the force you need, or the force of gravity on the object, or the force you need to hold that object up. Now, anywhere on Earth, weight is pretty much constant, but the main thing is when you're asked for a weight in engineering problems, the units need to be in newtons. You need to calculate the force. In everyday life, mass and weight are the same. In engineering, they're not. Two different things. Weight, you're looking for a force. Mass, you're looking for kilograms. So let's see a few more examples. Let me get rid of my scribblings. A few more examples of how to calculate weight. So the examples we've been asked to look at, I'm going to calculate 3 different weights from masses. And we've got a 1 kilogram mass, we need to calculate that, a B double truck, which is this big truck shown here. It's the one with 2 trailers, it's called a B double, and also a structural bolt, so something a bit like this. Now the bolt itself is just that bit. This is the nut, this is a washer. Okay, so let's start with the first one. Calculate the weight of a 1 kilogram mass. Bit of a trivial problem, but worth doing anyway. So first thing we do is just write down the equation or the question in short form. So we want a 1 kilogram mass. What's the weight? Okay, first thing is write the equation. So weight is equal to mass times acceleration due to gravity. What do we know? We know G, acceleration due to gravity, is 9.81 meters per second squared. And we know the mass is 1 kilogram. Stress this a couple of times in this equation, unless you're being sneaky and finding a shortcut. The mass must be in kilograms. We're already in kilograms, so nothing to worry about there. So W equals M times G. That's just equal to 1 kilogram times 9.81 meters per second squared. So it's 9.81, and it's a force. We're talking about weight, it's a force, so our units are newtons as long as we've used kilograms here. So as long as we're using kilograms for the weight, then this is going to be in newtons. Now, to do a rough check on this, what you usually do for rough checks or for estimations is just to say that 1 kilogram is approximately equivalent to 10 newtons. So you've got 9.81 newtons is the exact, 10 is approximate, and so we're on the right track with this one. We'll just underline the answer. In fact, we'll just do it properly and just say 1 kilogram mass weighs 9.81 newtons. Okay, let's have a look at the second problem. So we've got a B double truck with a mass of 55 tons. Some alarm bells should be ringing already because we've been given the mass in tons, and I've already said this equation, you need to use kilograms. So let's work through this one. So we've got 55 ton truck, and we want to know its weight. Okay, again, first thing, write down the equation. So weight is equal to mass times acceleration due to gravity. What do we know? We know G is equal to 9.81 meters per second squared. And we know the mass of the truck is 55 tons. But I'm thinking ahead, and I know for that equation I'm going to need kilograms, so I'm just going to change that to kilograms. 1 ton is 1,000 kilograms, 55 tons is 55,000 kilograms. Now we're good to go. So W equals M times G, which is equal to 55,000 times 9.81. Let's do the calcs on that. I think I've closed my calc pad. Let me open that up again. It takes a little minute. Okay, so we've got 55,000 kilograms. For this little calc pad, better not leave a space, times 9.81. So 539,550. I'm just thinking about how to round that. And so we want 3 significant figures because we use 3 significant figures in our acceleration due to gravity. So it's 540,000. So 540,000 newtons. Now, self-respecting engineer's not going to leave it like that. I'm going to find units that make for nicer numbers. So 540,000 newtons, 1,000 newtons, just a kilonewton. So we want to do 540 kilonewtons. We've got an answer. Now, you can take a shortcut here, but be careful that you don't use it in the wrong place. What we can remember is that we've still got W equals M. Let me just put this in green because it's not part of the main answer. So we've got W, too fat. So we've got W equals M times G. Now we could just have used tons here. So we could just have said 55 tons times 9.81 meters per second. But what we have to remember is, if we've used tons here, we have to use kilonewtons in the answer. So 55 times 9.81 is just going to be 540 kilonewtons. So tons, and this must be in kilonewtons. Okay, we can check our answer here just by saying, well, again, gravity is approximately 10 meters per second squared. So if we're using kilograms, we should just add a 0 to that. 55 or 550,000, which is roughly what we're getting. So 550 kilonewtons. We're in the right track, so that looks about right. I'm just going to take away those underlines. And then we've also got the same answer when we've done it by the shortcut. So then just write our answer in full. So 55-ton truck weighs 540 kilonewtons. Underline it so you can find it. One more example to go. Let's go through this one pretty quick. We've learned everything we need to know pretty much. So this is part C. We want to know the weight of a 100-gram structural bolt. So 100-gram bolt. We want to know weight. Just move the page up a bit. So first things first, write down the formula. W equals M times G, mass times gravity, and mass is in kilograms. So let's write down what we know. The mass is equal to 100 grams. Thinking ahead, we're going to need kilograms, so 0.1 kilograms. Gravity, acceleration due to gravity is 9.81 meters per second square on Earth. So therefore, W equals M times G, which is equal to, need kilograms, 0.1 times 9.81, which is equal to 0.981 meters per second squared. What's the units? It's a force because we're doing weight. It's newtons. We've used kilograms, so we're in newtons. No real shortcut here. Newton's pretty much the smallest unit of force that used in engineering and construction. If you're doing really fine work, you might get down to millinewtons in science, but not so much in engineering. That's our answer. I've underlined it again, but we should really write it out in short form. Our full answer. 100-gram bolt weighs 0.981 newtons. So again, we're writing out answers in full and underlining them so they're easy to find. So this is in part for other people reading your calcs. But what you find is on site, when you're working on a job, you might have done calcs a couple of months ago. You have to go through them to find a number you need. Someone's asking for it on site. So it's really in your own interest to keep them as neat as possible. Okay, let's move on to the next example.